Hi and welcome to Concept Based. I'm John Hepworth. This one's a Year 11 Advanced video. You guys are now at week 4 and you might find that there's a bit of a shift that takes place in the classroom. You may have found that you were struggling with the amount of algebra that was being presented at the start of the course. And then you stepped into a new concept, this idea of a function as opposed to a relation. But then things may change a little bit in the classroom. There might be a fair bit of revision that actually begins. You might then start delving into linear functions, quadratic and cubic functions, reciprocal functions. And with that being the case, you're going to be going over content that you've covered extensively in year 10 already. And you might feel like the pace comes off a little bit and that you have a chance to breathe. So if your scope and sequence is following the one that I'm following, which it may not be, then that may be your experience this week. So today's video is going to be a little bit easier. However, I'm going to do this video the way that I always do these videos, and I'm going to talk about concepts, not just procedures. This question's a very easy question procedurally, but unless you have the underlying concepts of what's going on, then again, being able to check that your algebra is accurate as you go becomes challenging. So what I'm going to do is I'm going to do this question two different ways. I'm going to do it visually, and then I'm going to do it algebraically, and then I'm going to change the question to something that is more of a twist, something that you might be more inclined to see in the HSC, where it's not just a straight up procedural question, but there's some sort of twist on the question that makes you have to use a range of skills to be able to solve the problem. So this question, find the equation of a line with the gradient of 2 that passes through the point -1, 3 and determine if 4, 11 lies on the line. So what we want to do first of all is just look at it graphically. As I always say to my students, if you can sketch something first, that'd be great. It gives you an understanding whether you're in the right ballpark. So let's go and sketch something. We know that this goes through at -1, 3. We know that it has a gradient of 2, so it's going uphill like this. And then later on, we're going to determine whether or not it's going through 4, 11. 4, 11's way off my graph. Often you'll find that that will happen, and you need to be checking whether that point up there goes ahead and lies on this line. Okay. So how much of this can we actually solve graphically? Can we do the whole thing? Well, we can. So for starters, we know that it has a gradient of 2. So every time we go across 1, we're going to go up 2, right? That's what makes a gradient a gradient. Whenever the gradient's negative, it goes down. Whenever it's positive, it goes up. It never runs left. We're always reading it from left to right. So if you're still getting confused with, well, why isn't the negative on the bottom of the fraction? Or what if the negative's on the bottom of the fraction? All we really care about is that we're always reading left to right. So we always go 1 across, or however many across are in the fraction, and then we go up or down, and that's depending on whether it is positive or negative. This one is positive 2, so we're going to be going up 2. Now, it just so happens with this example, when we go across 1, we hit the y-axis, and we go up 2, we're going across the y-axis at 5. So we actually have enough information now to have an equation of a line, because we know the equation of a line is y equals mx plus c from, again, year 10, even earlier actually, but year 10 definitely is where it is formally solidified. And in that, we have m as our gradient and c as our y-intercept. And we were given the gradient in the question, so we could fill that in. And we just worked out what the y-intercept, so we could fill that in. So we actually were able to find the equation of the line graphically without really doing anything in terms of an equation. And then the next part is to check whether or not it goes through 4, 11. Now, I'm going to do that algebraically later, but I'm going to do that graphically right now. So now we have a situation where we could either consider this point or this point. I'm going to consider the y-axis one. So we're at 5, and the x value when we're at 5 on y is at 0, and we need to get across to 4. So we're going to run 4, but this gradient is 2. So after running 4, we are going to rise 2 lots of that. So we're going to rise 8. So we're going to go up from 5 up by 8. And if we go up from 5 by 8, then we're going to end up at 13. Now 13 is not the point we are looking for. So we can say graphically from all of this, without ever writing anything about x1, x2, y1, y2, any gradients, anything, we can just do the whole thing visually. And we can say, well, no, that 411 definitely does not lie on the line. So we have an understanding. We understand the concepts of what's going on in this linear equation. Okay, so that understanding can underlie the algebraic techniques that we use to go ahead and find this out. So we're asked to find an equation line that goes through a certain point. So from this comes an equation of a line. And so the equation of a line that we can use is y minus y1 equals m outside of x minus x1. Now, I'm never really just a fan of students remembering equations and not understanding where they come from, how they work, what they're all about, and so forth. So I would highly recommend that if you're looking at equations like this and you think, oh no, I'm just really not sure about that equation, then I would recommend going back and having a look at derivations, why they are what they are, how come they work the way that they do, and just making sure that you feel confident about the equation when you're going to go and use it. But this is the equation that applies in this situation. So the reason why this is the equation that applies is because we have a point, x1, y1, and we have a gradient, m. So we can go ahead and use this equation. So with that being the case, we're now going to go and put those values in. So y1 was 3, m was given as 2, and x1 was -1. Now, when I write -1 into an equation, I always add an extra set of brackets because I don't want to confuse myself. I want to know that the -1 was the substitution in and that there is a minus in front of that. So obviously I'm going to change that negative and a minus to a plus, so I don't make an algebraic mistake. So we then go and we get y minus 3 equals 2 outside of x plus 1. Nice and easy. And then we expand the right-hand side to x plus 2. And then we take the 3 over and we get y equals 2x plus 5. Now, you can see that there's quite a few lines of working there to do this algebraic technique of solving this question before we get to this point of 5. Now, one of the lines that I mentioned where an error could occur is right here. Say we did make a mistake there and say that we thought it was x minus 1. And then when we added it across, we would have got a 3 here. And as I've said before, how would you ever know that that 3 is not right if you're not coming at these sort of questions from a conceptual understanding? You should be able, from your conceptual understanding, identify that 3 there is wrong immediately. And why is that? Why would I know that 3 is definitely wrong? Hopefully you thought to yourself, because the y value of 3 was back in this point at -1, 3. The line can't still be at 3, at a height of 3, when it's moved along 1, especially when it has a gradient of 2. It has to have gone up somewhat. So just whacking things into formulas and having no relation of the solution to what the concept is of what's going on, it just opens you up to making what students often refer to as silly mistakes. But it's more than a silly mistake. It's sure, you make a silly mistake because you do minus minus and you get a minus. But it's worse than that. You should have realized that 3 made no sense because you had a point that wasn't on the y-axis that had a y value of 3. So there's no way this line could have a 3 there. So next time you find yourself getting an exam back and you go, oh, I made a silly mistake, that should be a trigger for you to go, was there something more that I could have understood that would have ensured that the algebra that I did had some sort of checking mechanism so that I knew that I had made that silly mistake? Okay, so we've now got this equation of the line y equals 2x plus 5. We now need to go and check whether 4, 11 lies on that line. So we go and substitute the values of 4 and 11 in. 11 equals 2 times 4 plus 5. On the right-hand side here, we're going to get 8 plus 5, and then we're going to get 13, and 13 definitely does not equal to 11, so therefore the point does not lie on the line. And you can go ahead and state that, therefore 411 does not lie on the line. So there we have it. We are able to solve that question, as you saw initially, graphically and then algebraically. Now I know these are easy concepts from year 10. And again, you know, Mr. Hepworth, why are you doing this really long-winded way of having these concepts? It's not the fact that you would fully work through all of the concepts in your HSC paper, but we need those concepts going through your brain while you're doing the question. So practicing having both ideas just gives you so much better grounding, so that when you are doing the question and just attack it algebraically, at the same time you have some checking system going on inside of you that's making sure that your answers do make sense. Now, what if this question was a little bit tricky? What if it, when you walk into the HSC and you know that you've got linear relationships completely under control, does anybody get concerned that I just rub out so slowly with all those things rather than go and circle the working and just delete it? And why don't you just do that, Mr. Hepworth? Okay, so let's make some changes to this question and see what we can do this time. Let's say now that the equation of the line has a gradient of m, it passes through the point -1, 3, and it passes through the point 4, m. So that makes the question significantly different, because now with this question, we don't have all the numbers that we had before. And students who think about linear functions in terms of tables of values, where they go across one, up a certain amount, across one, up on a certain amount, will become a little bit lost, because now we've got a gradient of m. So we don't go up by a certain amount, we just go up by m. So that can be a little bit hard now to think of, well, what does that graph look like? But it is achievable, okay? So at -1, 3, we have a point, and we're going to have a gradient of m, and it's going to hit some other point at 4. So let's have a think about whether or not this is actually possible. So let's say we drew a line like this, and it hit this 4 point here. Think about that. If, let's say, we did that with the most basic gradient of all, the gradient of 1. If we had the gradient of 1, it would go across 1 and up 1. So it means it would have gone across 5 and it would have gone up 5. And we would have hit this at 4, 8. So we can't go across 1 and up 1 and then hit it at 1, because that's what this question's actually saying, that this 8 would need to be a 1 to work. You notice that it's a lot further below where we end up. So in fact, we would even need a gradient that is bigger than 3 to even be above this point. So what if we did have a gradient that was bigger than 3? Let's take into consideration a gradient that's significantly bigger than 3. Let's make it 10. So now I'm just going to draw the same line, even though obviously it's really a lot steeper. Let's say a gradient of 10. So here we are at the point -1, 3. We're going to go across to 4, so 5 steps. A gradient of 10, 5 tens of 50. So we're going to go up by 50 and hit this point here at 453. Now, what did we say the gradient of this line was? We said a gradient of 10 this time. And look where it's hitting, 53, not even close. So before we go and do this algebra, we can actually realize that the idea of getting a positive solution out of this question doesn't actually make sense. It doesn't work on the graph. So again, would you have that level of conceptual understanding underneath while you're doing the algebra? Maybe, maybe not. But kids that are achieving band 6 results, this is the sort of flexibility that they have in their thinking that can fault check their solutions and see whether or not it makes sense. What about if something was negative? If it was just a little bit negative and it went through somewhere like here, this makes no sense because this is for something positive, but we're talking about a negative gradient. And that makes no sense. So therefore, the only way that this line can actually work is something that looks like this. We need the gradient to be negative, some negative amount, and go through at some negative point. Let's just check -1. So if it's at -1, we're running 5, we're going down 1 each time, so we're going down 5. From 3 means we go down to -2, so 4, -2. It's not right, but it's close. It had a gradient of -1 and we went through the point -2, so we can sort of expect it to be around here somewhere. Again, I'm not expecting you to draw all of these at the start of the question, but I do want you to realize or aim for some sort of understanding about what would and wouldn't make sense. You may be able to come to the realization of this question by thinking about this in your mind, that a positive m here makes no sense. Okay, so let's go and do the question. So we need the gradient formula this time. Now, selection of formulas needs to be amazing in advance, because if you go and use the wrong formula, you're not going to get an answer out of it and you're going to have wasted time. So picking the right formulas, obviously, we need to be doing that. And I would really prefer that you remember all of the linear relationship formulas because it just makes it faster. This one 100% makes sense from our rise-run triangle, our y2, I'm too far off the screen there, our rise-run triangle, our y2 over minus y1, x2 minus x1. If you're not sure about this and why it is that formula, again, go and have a look at your year 10 notes and make sure that you do grasp these formulas deeply so that you are able to use them in your concepts in year 11. Okay, let's sub in. We are told that the gradient is m. Our y2 value is also the value m, and our y1 is 3. Over x2 is 4, and y1 I'm going to do in brackets again at -1. So now we go and do algebra. So m equals m minus 3 over 4 minus -1 is 4 plus 1, which is 5. And we get 5m equals m minus 3, which means 4m equals -3, which means m equals -3/4. This is what we expected, some sort of negative gradient that's going to work out to be hitting that point at some small negative value. Now, where could we have gone wrong? At the exact same place again. We could have added one. We could have added it together and got a, subtracted it, and we could have got a 3, and then we would have got 3m, and then we would have got 2m, and we would have got a slightly negative value. And so we could have done it wrong from that. With that different negative value, would we be able to pick that up? Maybe, maybe not. What we should definitely be checking here is that it at least makes sense for the point that it does go through. So if we've now got y equals -3 on 4, x plus c, we want this to be able to work for the points that we have. Now, if we do have a gradient of -3/4, we can, again, fill this c in. So we know that it's going to go down 3 and run 4, but it's going to go down by 3/4 when it runs 1. So if it was at -1, 3, it's going to be at 0, 2 1/4. And now we can go and put our x values and y values in and see if it works. Does 3 equal -3/4 times -1 plus, I'm just going to write this as an improper, 9/4. I find working with improper fractions much easier, particularly in linear functions. So now we're going to, well, we can just tidy up that middle bit. 3 equals negative times a negative is a positive, 3/4 plus 9/4. And 3/4 plus 9/4 is 12/4, which is happy days because 12/4 is 3, which means the point is on the line. So it looks like our gradient is happy for going on that line. We could have checked the other point, possibly even more important, because we defined that one for its m, and see if that one's true as well. That might be one you could do, and it will be true because -3/4 is definitely the correct answer there for that one. So here we are again at quite a long video for two relatively straightforward, simple questions that are not going to be worth many marks in the HSC. 2 maximum. So we definitely don't want to be taking 20 minutes with the questions. The point is, pardon me, the point is that we really want to make sure that we have a deep understanding to be able to cross-check our answers so that if we make an algebraic mistake, that we have some sort of way of identifying that we've made it and we don't get our test back and just say, oh, another one of those silly mistakes.